Mark Robert, everybody.
It's actually Matt, but I won't hold that against you. All right, guys, welcome to Ruxcon this year, and thanks very much for attending the presentation. Many of you are probably aware that we did a similar sort of thing last year, which was an introduction to GNUradio and our implementation of the APCO P25 standard in that project. So, yeah, you just bear with us. Some of the slides will be similar because I need to give a bit of background so you know where it's all coming from. If I just jump into the new work that we've done, it's not going to make any sense to anyone. So if you've seen the presentation last year, just bear with me, all right? So anyway, we'll start off about myself. I'm an amateur security researcher. All of my efforts in this project have been self-funded by my day job. I'm also a licensed demo radio operator, which is a key part of the project. Every single test and every single bit of proof of concept code that we've written and all the work that we've done has been using the amateur radio frequencies under the experiment license. So essentially we're just using it for test purposes, and no production or actual real frequencies have been used at all whatsoever. For my day job, I'm a systems infrastructure and platform manager, which is just a usual sort of title you get when you work in a large corporate, which essentially is just a systems administrator role. And for my hobbies, I like to fly aerobatics when I have the spare time and money, which is almost never these days. And I don't normally look like David Boone or Chopper Reed. I'm just doing November, so bear with me. Anyway, I realise it's not a dating site, so I'll move right along. So what this presentation will cover, basically I'm going to go over a brief introduction to software radio and how the P25 software stack works. And we'll then use that information to then see how some of the P25 protocol implementations have some little flaws that can be used to realise some practical attacks. And we're also going to discuss some of the fixes too, because a lot of the implementation flaws have patches that people just aren't implementing because they don't understand the technology. And the obligatory disclaimer here, what this presentation is not, it's not going to be a guide to hacking your local public safety P25 communication system. When we wrote the initial synopsis and it got into the Ruxcon guide, I sort of went back and read it, and it kind of appeared like we were going to be hacking things for real and make it look like we're out there to do bad things and release tools and cause mayhem, and that's absolutely not what this project is about. It's a white hat project that we've basically done. It's self-funded. It's been sponsored by NICTA and a couple of universities, and the whole point was to write a few academic papers, get them published, and get a bit of knowledge out there about how to protect P25 systems in the real world. So yeah, just one more. I just need to reiterate this second point. Some of the attacks in here, we have written tools in private to do Inhibit attacks. We have actually done some DOS attacks on our own radios, but they're not going to be released. The software and all those tools are all proprietary, and they're not available anywhere on the web or anything, because basically we're not going to help bad people do bad things, right? It's a bit back to front, I apologise. So the P25 project, this is where it all sort of started back in about 2008, I think the idea initially came out about. The website, if you can sort of see the yellow on white there, it's a little bit hard to read, but it's sedition.org.au. We're sort of poking fun at the anti-sedition laws that John Howard introduced a while back, so don't read into that one too much. If you hop on the Yahoo Groups list, look for OP25-dev, and you can get access to our entire mail repository, and all of the information is in there, the entire history of the project and what's been done over the years. We've got about 200 members from around the world, and there's about 8 core developers. So I'll just mention some of the key people. There's Max Park. He's a brilliant DSP and signal processing guy that's in New York, and he's been absolutely brilliant in this project. He's devoted so much time and effort on his own behalf just to get us to where we are. There's Steve Glass, who's my co-presenter, who is notably absent. He actually had a family emergency and couldn't make it, so he was the project founder and leader originally, and the whole thing was basically set up as a way to get people interested in P25 and to basically get some papers published for his PhD thesis. There's Mike Osman. He wrote the Wireshark plugin, so we can use Wireshark to sniff traffic and sort of go in and analyse it and see what's happening, read all the particular values, the key IDs, see how the traffic actually looks and look for implementation flaws and bugs. And of course there's myself, and there's Balance Sieber, who's just down here that's been helping out. He contributed to OFB encryption support and decryption, which we'll be demonstrating later on. So yeah, P25, as I mentioned before, it's supported by NICTA, which is the National Information Communications and Technology Association. Basically, NICTA's goal is to be the world's #1 IT research organisation in the world by 2020. And they're sponsored by some of these people down here. For example, the Department of Broadband Communication and Digital Economy, and more notably, University of New South Wales and Griffith Uni, which is where the project actually started. So, who uses P25? Well, there's various Australian federal law enforcement agencies, 3 and 4 lettered, which I'm not going to mention. There's the usual state police forces, New South Wales, Queensland, South Australia. I think Victoria's using it as well down here. There's also various airport fire brigades use it. There's the Victorian MMR, which is the mobile radio network. All emergency services in the metropolitan area are on a P25 trunk system. So if you don't know what trunking is, it's kind of like a mobile phone network. You don't have a dedicated frequency that people talk on. The radio is basically camped to a control channel, which then tells the... you're right. It then tells the radio to go to a frequency as allocated. So basically, it's used to conserve spectrum. If the radios aren't constantly on a dedicated channel, it's only being used 10% of the time. That channel can then be allocated to other emergency services, so you get consolidation and cost savings. So yeah, the government and Motorola are really big on that trunking technology because it saves a stack of money. And also South Australia GRN is the same. So why should we care about this, right? Well, we need to ensure that public safety agencies and officers continue to do their jobs safely. That's number one. That's the whole point of having P25 encryption. At the end of the day, it's basically there so that people can go and do their jobs. They can coordinate drug busts. You know, they can go and they can communicate effectively and safely, so that they know that no one's listening in and the criminals aren't going to be one step ahead of them. And also, the second part of that too is it prevents public information from being disseminated. For example, if you get pulled over for a drink driving, or you get pulled over, I don't know, snorting cocaine while you're driving down the freeway at 180 k's an hour. It's not the sort of thing you want to be public, right? So when it gets called in over the police radio network, your information is secured too. So it works both ways. It's not just us that's concerned also. Since we initially started the project, a group of researchers in the US have started looking to APCO 25 as well. It's a team headed by 2 guys, a guy called Sandy Clark who was doing his PhD, and famous cryptographer Matt Blaze. Who knows the name Matt Blaze in here? A couple of people, okay. He was big on busting the Clipper chip years ago. President Clinton wanted to put an encryption chip in every single x86 CPU that it did all the encryption for you. So SSL and all of that was all going to be thrown out, and this Clipper chip was going to do all the encryption. It was going to use keys that the US government fed to you as needed. So that idea didn't last too long. And also, there's a quote here that sort of summed it up. Matt Blaze sort of looked at the state of the art in software-defined radio and the way the technology is going. And he said, it's going to be someone somewhere creating the Project 25 jamming kit, and it'll be something that you download from the net. We're not there right now, but we're close. And I guess it might sound a little bit alarmist, but essentially he's just concerned about the state of progress in software-defined radio technologies and the development that people are doing in that area versus the 20-year-old technology that's P25 and the number of flaws that are in it. He's sort of concerned that there's a bit of a convergence between those two areas that could result in bad people doing bad things. So just a quick one. I know we've been over software-defined radio at this conference already. So basically what it is, you've got your antenna here, which is essentially just the input to the software radio box, which is the USRP. In the front end, you've got some flexible RF hardware which performs down conversion. And the reason for that is the frequencies that we're actually listening to are up around 400 or 500 megahertz. Now, when you want to digitize frequencies that high, you need a minimum sample rate of double the highest frequency you're listening to. So if this thing here is tuned to 400 megahertz, that means your ADCs and DACs need to run at least 800 megahertz, that's way beyond the state of the art at the moment. Currently, ADCs go up to maybe about 100, 200 megahertz for an expensive one. So we basically use this front end to convert the 400 megahertz frequencies down to baseband, which is essentially 0. Then we convert it and digitize it using the ADCs at 100 megahertz. That gives us up to 50 megahertz worth of bandwidth. And all this sort of cruft on here on the left is basically it's just a bunch of stuff in the FPGA that gets the numbers out of the USRP and into the host. So yeah, once the baseband has sort of come to this side of the graph, it's essentially ready to be inputted into the computer for processing. So in the analog domain, that's a basic sine wave that everyone knows. It's basically voltage on the vertical axis and time on the horizontal. And this is what's hitting your antenna. You've basically got an electric field which is exciting electrons in that antenna, which causes a voltage at the end of it. When you digitize it, it sort of looks like this. You get these little steps because you're limited by the granularity of the ADC. So you can see there is loss in the digitizing process. That's why you need to have as many bits in your ADC as possible. It's the exact same reason why your old 8-bit Nintendo audio sounded really grainy and sort of granular. Each one of those steps creates harmonics in the signal. It sounds really nasty. So, CDs went to 16-bit, and then you can get some 24-bit sound cards, and the quality's just gone up as those steps got smaller and smaller, and the waveform could follow the original one more closely. So these are the USRPs. This is basically the crux of software radio. The top one's the USRP1, 8 megahertz bandwidth, which is quite a considerable chunk. It's the equivalent of 6,400 P25 channels at once that can get digitized and put into the host. It hooks up via USB 2, and it's essentially limited by the USB 2 bandwidth on that bus. Costs about $1,200. The newest, latest and greatest one is the USRP N210. It's hooked up via gigabit Ethernet, which has got considerably more bandwidth, and it can do up to 20,000 P25 channels at once. And the cost goes up again to about $2,000 US. So, on to the good stuff. Cryptanalysis of P25. The whole basis of the cryptographic work and the papers that we've published is the good old-fashioned known plain text attack. Basically, all it is we're looking for a part of the message that's been encrypted, and we know what the encrypted contents is. During World War II, they called it a crib at Bletchley Park, which was the UK's main post for doing cryptanalysis on the German transmissions that they were basically intercepting. And they were looking for known words. The way they actually cracked, I think it was the Enigma code, I'm not sure, but they did it based on weather reports. I think at 9 a.m. every morning, the Germans would send a weather report, and the first word in it would be weather in encrypted form. So all they had to do was just try every single encryption key in every permutation until they found weather. Bingo, the whole message appeared. That's how the system was cracked. And due to the regimented style of military communications, there were lots of cribs, lots of known plain text, because the military is regimented, so they do the same thing the same way every single day, and it's all done to a specified format. So once they figured out the word for weather, the whole thing was basically owned. So yeah, sure, that's a good story, Matt, but how does this relate to P25? Well, we've got to take a bit of a step back and look at how P25 actually digitizes and sends voice traffic. P25 is a 4800 baud signal, and it gives an aggregate data rate of 9.6K, okay? When P25 is encoding voice traffic, the voice codec slices the voice traffic up into tiny little frames which are 20 milliseconds each. And they're grouped into two types of frames called LDU1 and LDU2, logical data unit 1, logical data unit 2. Each one of those LDU1s and 2s contains 9 slices which are actually known as IMBE code words. Each one of those vectors or code word, it contains pitch and intensity information, voiced and unvoiced noise, amongst other things. So it conveys the current pitch of your voice, the loudness, the intensity, the tone bar, and there's also voiced and unvoiced noise. So say you're in a car and you're driving, the sort of background wind noise can also be transmitted using that the unvoiced code words. And also, this is an interesting part of it, the vectors are protected by varying amounts of forward error correction, depending on how important the data is that's being protected. So this is the anatomy of the LDU1 and LDU2 frames. You can see at the top here you've got 1,680 bits. You've got the 9 voice code words. Each one represents a 20 millisecond slice of voice. It goes through a bit of interleaving, which sort of mixes it up. Then it goes through another step where it gets exclusive ORed with a pseudo-random sequence. And the whole purpose of this, it's not for security or to obfuscate anything. It's to protect against fading and noise on the channel. So it adds entropy into the channel so that there's no DC bias and things like that. It makes the transmission a little bit more easy to decode and nicer on the other end. You see down the bottom, there's U0 to U7. What are these? Basically, what these are the contents of each code word. Each one of these little slices consists of these 88 bits. And you can see the most significant ones have the most error correction, which are the bits in black. So they've got the most protection. In a noisy channel, say you're on the edge of coverage or you're getting interference from a nearby station or whatever, the extra amount of error correction on these particular code words ensures that they're going to get through and cut through the noise. On the end here, you've got U7, which is the 7 least significant bits, and there's no error protection whatsoever on that channel. On this particular variable, it's essentially unprotected. And just make note of that because it comes back into the security analysis that we'll go through in a second. So you can go back and see each one of these frames is 180 milliseconds. When someone makes a transmission, they obviously have to end it at some point when they're finished speaking, right? So you key in the radio, making a conversation, and then you release the key at the end. Now, when you release the key in the end, you have a 1 in 9 chance of being right at a frame boundary, i.e. here or here. Every other time, and this is 99% of the time, you're going to be somewhere in the middle of a transmission. So what happens when you dekey the radio at that point? Well, it inserts standard defined silence frames which are a known value. These values are always exactly the same. They're defined in the standard, and the P25 standard actually states that to be compliant, your radio has to transmit these values in that location. Right, so there's our crib, there's our known plaintext. That's our version of the known plaintext attack. And you can see it right here. This is a clear transmission. This is the first frame in a transmission. This is a test that I did at home. I just keyed down the radio and released the key at the end. You can see the first 4 frames out of the whole 9, 6C42, 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 6C42. So there's our known plaintext. And also once you move ahead, you've got the exact same thing at the end. And it's the end ones that are actually more useful to us from a security point of view. And I'll come on to that in a second. You will notice there's a few errors in there. For example, that E is actually an A down there, and that was due to a bit of noise on the channel. So how does DES-OFB encryption work? This is pretty much it was the de facto standard a couple of years ago for public safety encryption. It's since been replaced with AES 256 and various other algorithms which are a lot stronger. So what it is, you've got a bunch of keystream. DES-OFB works by encrypting a random number, and then you keep encrypting that number 28 times, and that creates the keystream across the top here. DES works on 64-bit inputs and 64-bit outputs. So that's 64 bits, that's 64 bits, and that's 64 bits. And each one of those, you encrypt again with the key, you encrypt again with the key, and that's how you form that stream. Down the bottom here, you've got those last 2 voice code words, which are the 2 silence frames that we saw down here at the bottom, right? So we know what these are. We can guess what this is because it's only small, it's only 16 bits. That's trivial on a modern PC to crack. So all we have to do is XOR this with the known value, the known plaintext, with the actual keystream that we see, because an XOR, this exclusive OR operation is reversible, right? Going this way gives you the output, and going back will give you the input. So if we know this, we can deduce the raw keystream. Once we know the keystream, you can tell that this was the DES input block, that's the DES output block, and it's trivial. All you need to do is get a bloody big machine and try every single encryption key until you find the right one. You basically encrypt this block here with random numbers until you find this one on the output. And that's essentially the basis of the DES-OFB attack. It sounds simple when you're talking about it up here, but DES is actually quite a strong cipher. It was built very well back in the 1970s. NSA and IBM collaborated on it. They really worked hard because they knew it was going to be the financial standard when the IT boom sort of eventually came in years to come. So they really, from a cryptographic point of view, it's quite strong. The cipher has very few breaks or flaws inside it. The only thing that lets it down is its small key space. It's only 56 bits. And Moore's law caught up with it eventually. You can test 56-bit key space in a reasonable amount of time now. It gets better. Let's say your transmission is one that ends right on the frame boundary. So let's say, just by chance, we've dekeyed right on the end here, and that means that there'd be no opportunity to insert those silence values, right? That means that all of this is going to be valid voice traffic, and you don't know what that traffic's going to be. So you could go out and waste a whole bunch of money trying to crack these values with your huge, expensive supercomputer and waste your time. It seems that Motorola wanted us to crack it. If that happens, if you end on a frame boundary, you don't have enough known plaintext to be able to brute force an encryption key. You need 64 bits input and 64 bits output. If you've got only one silence value at the end, that code word's only 88 bits. We need 128 minimum. And that's where we enter US patent number 5220565. Selective transmission of encoded blah, blah, blah. It was originally published in June 1993, I think, and it was last updated earlier this year. So they're still worried about protecting that IP. What it tells us, when a message concludes there may or may not be sufficient additional voice packets to accommodate the required number of additional packets, which are the silence frames. In this embodiment, being the patent, 2 such packets must be sent. Right, so this patent forces them to add at least 144 bits of known plaintext silence at the end of each transmission, and all we need is 128 to actually retrieve a key. I normally take things as I see it, right? I'm not much of a conspiracy theory kind of guy. I'm fairly straight down the line. But this is too much of a coincidence. This patent essentially forces the protocol to insert enough plain text to be able to crack it every single time. Is it meant to be that way? I don't know. We'll probably never know. Yeah, you can see it sort of reiterates down the bottom here that if a message concludes and leaves only one voice packet, which is 88 bits, then the last packet will be sent with silence, and an additional frame will be sent with all 9 code words sent as silence, which is 180 milliseconds. It's about almost a kilobyte of known plain text. So you can take your pick as to what you want to use to try your encryption key recovery. So that's the weakness in DES itself, and that's pretty much the biggest thing we found with the encryption. The DES algorithm itself has been broken publicly since 1997. There are a number of big projects. There was DESCHAL, which when the internet was sort of booming in those days, it was sort of like a distributed application that people got onto. I think they cracked it in about a week. Then a couple of months later, EFF, the Electronic Frontiers Foundation, they created a custom IC and built a big cluster of these ICs. It cost them about $250,000 US. They cracked it in about 2 days by collaborating with the DESCHAL guys. And more recently, a bunch of university students in Germany created the Copacabana. It's got 4 times the power of deep crack, and it cost about $9,000 for them to cobble it together. And that was in 2005. So these days you can purchase off-the-shelf solutions that will brute force DES for you. There is actually a market out there for people that want to retrieve DES encryption keys, believe it or not. It is still a great expense though. Like I said, DES is quite a good algorithm. You can't really crack it effectively using modern Intel processors. It just doesn't work. It's more a hardware-based algorithm by virtue of the fact that it was developed in the 70s. So DES may be broken, but that doesn't mean it's cheap or easy by any means. This is a confidential price list I got from Pico Computing. They're probably the number one guys that do FPGA clusters and cryptography work in the States. And you can see right down at the bottom, for 56-bit DES, for a machine that will get through it in 2.41 days, it'll cost you $90,000 US. So it's not a trivial thing, right? You've really got to make sure that this information's of value to you if you're going to spend that sort of money. And it's actually quite impressive. It's testing 345 billion keys per second, which is, yeah, that's quite fast. So anyway, that's DES OFB. As part of the research, we found another cheaper algorithm, which is ADP. It's a proprietary cipher system. Not much information was available on it at first. All we knew is that it was suspected to be RC4 based and the key size is known. It's 40 bits, and contrary to what that says, it's got nothing to do with the US export rules. They're trying not to compete with their own high-tier encryption products. So we eventually reverse engineered the cipher too. We knew it was RC4, so it was just a matter of getting an RC4 engine. I think we pulled it from the OpenSSL library. Yeah, we did. And then we created a transmission with a known key. We used that known key to generate streams in the OpenSSL library, and then we basically shifted the 2 streams until they matched up, and then we figured out how the cipher was working from that. And this is basically it. There's an initialization vector at the end which is added to add entropy. It prevents time-memory trade-off attacks. So you know that you're not going to get, if for the same known plain text, you're not going to get the same ciphertext because every time you transmit, this initialization vector is different. It's called an IV in this context. It's also called an N-once or a nonce, or it's kind of analogous to salting in password files. So yeah, that's ADP. That's just, pseudo algorithm of how it works, so we'll skip on from that. We've sort of been across that already, so I'm not going to go over it again. The ADP key recovery, it works the same way as the DES OFB does. It uses the known silenced code words at the start and the end of each transmission. And you basically just XOR with the known value, and that produces the key stream. And you try every encryption key until you find that key stream, and then you know you've got your key. There are a number of different approaches these days. You can use FPGAs, but there's really not the gain there is with DES. An FPGA only works out to be a couple of times faster than a CPU. Unless you scale it up, you can buy a lot of FPGAs and run them in parallel. And unfortunately, Steve's not here, but he actually did all the work on implementing the GPU stuff in NVIDIA Tesla, and that was quite interesting stuff, but I'm really not across it enough to give you a good, in-detailed analysis of how it works. But basically, using 2 graphics cards, I think the encryption key was recovered in about 6 days. And that sort of gives you an idea of what the logical flow of the GPU grid is. The problem with RC4 is the state memory. Each GPU core in the NVIDIA cluster, it only has access to the same shared memory of 16 kilobytes. Each RC4 engine needs 256 octets of state memory to keep track of where it's at. So we can only run 63 threads at most. You basically divide the 16K by 256 and you end up with 63 threads. And that only represents, I think, 6% CPU utilization on those NVIDIA cards. So it's basically memory limited. All right, so that's the ADP stuff. Now, there's some stuff that we worked on too with Inhibit attacks. P25 Inhibit is, it's used to inhibit stolen or lost radios or nuisance radios on a network. If someone pops up on a network and they're abusing people, or they're trying to, imitate the cops, or, jam the channel or something like that, you can send a special Inhibit packet in the P25 spec, and it kills the radio completely. The display is dim, the keys don't respond, it goes completely idle, you can turn it on and off, it won't respond to anything whatsoever. All it's doing is sitting there in an idle state, and it's basically listening to the channel, waiting for an uninhibit command to bring it back to life, just in case it was an accident that was inhibited in the first place. The problem with it is, it's got no authentication whatsoever. So if you've got a transmitter that can transmit P25 traffic, and you fire it up on that channel and send it to the radio ID of this radio here, it'll die. It doesn't challenge. There's no challenge response. There's nothing. There's no handshake whatsoever. It just basically kills itself. So it could be used for a pretty nasty DOS attack if anyone was that way inclined. It's easily spoofed. Basically, you just set the sender ID to whatever you want, and you set the target ID to whoever you're targeting. We also noticed that in the specification there's an all-call address, like a broadcast address for P25. So what happens if you send an Inhibit packet to that address by mistake? We didn't want to test it. Not even on our own radios. We thought, no, that's, we didn't want to know. So yeah, there's also one further caveat. In simplex networks, you can turn it on or turn it off. It's an optional feature if you're simplex or you're using a repeater. If you're on the trunking mode, it's mandatory. You have to have it to achieve compliance. So how did we actually recreate that attack? Well, this is a block diagram of our P25 transmitter. You've got a capture file and a PCAP source file, and that's where the actual traffic gets generated. Modulator, symbol filter, FM modulator, an amplifier, and finally the transmitter at the end. And that's pretty much the entire block diagram. As an encoder, this is the first bit over here. That's the software that actually creates the packets that we transmit. That's where you can specify your target radio ID, you can spoof the source ID, and you can also specify the target network ID, which is, the network ID is used to differentiate different types of networks. It's sort of to separate different users running on similar systems. That packet creator and framer that creates these packets, that's the proprietary bit of software that we're not actually going to release or let anyone have, because, yeah, we don't want people to be able to do that. It's just for us. The next attack is, in a secure network, accidental clear transmissions. In a cryptonet, a bunch of encrypted operators hear unencrypted transmissions too. So if you've got two people, one running no encryption and the other one is encrypted, as long as they're both loaded with the same key, they can't tell the difference between who's encrypted and who's not. There's no real indication on the radio to say, hey, this guy over here is not encrypted, but you are. So if you tune into various channels, you will hear operators operating in the clear even though their peers are encrypted. Since the end user, there's no perceived difference, right? They can't tell the difference. There's no real alerting on the radios, like I said, and therefore you get inadvertently messages get transmitted that aren't encrypted. This is part of the Matt Blaze and Sandy Clark thesis that was done at University of Pennsylvania in the States, and they basically talk about it here. They said that when they were monitoring this particular attack, they heard names and locations of investigative targets, including those involved in organised crimes, information relayed by wiretaps, plans for arrest, raids, and other confidential operations. On some days, they'd capture less than a minute, while other days they capture several hours of traffic. Yeah, so it's quite a big thing. I think it's probably one of the worst things that they came across. There is a way around it. In Motorola radios, you've got a technique called strapping, and it forces the user to be encrypted. If you've got no encryption key and you try to key the radio, it'll basically bonk at you. It comes up with an error. It comes up with a key error saying you can't transmit because the radio isn't key loaded. That's been there for years. Why isn't it being used? That's the question. It had fixed the problem, and apparently I heard some rumour or something on the internet somewhere, reading radio forums or whatever. There's some legacy attitude that if the keys get dropped, the radio will be completely useless. Apparently 20 years ago, the initial radios that had encryption in them were prone to losing their keys if the battery would become unseated for a few seconds. So apparently there's some paranoia around that, that the encryption key will get dropped and they won't be able to transmit. Next one's the unencrypted metadata attack. In the header and every second voice packet, there's encryption sync information, which basically keeps the encryption algorithm synced between the transmitter and the receiver. You can see a couple of the encryption algorithms down there that are in use. And it sort of sits interleaved throughout this LDU packet. See, unlike SSL where a handshake is performed and once trust is established, then you transfer your parameters, P25 blindly accepts whatever it hears. It's obviously bad from a security perspective because it leads to this attack here. Say you've got a group of users that are in a group, you've got, say, 5 people and they're all talking to each other encrypted, and they're all happy, there's no problems whatsoever, adversaries can't hear them, there's no issues. An attacker can come along and monitor that traffic, and using this encryption sync information, they can perform frequency analysis to determine who the network controller might be, for example, who's the base console by radio ID. They can't hear the encrypted messages, but once they know the encryption algorithm, the key ID and the network ID, they can perform a spoofing attack. All they need to do is send a transmission to the existing radio network with the same encryption algorithm, the same key ID and the same network ID. It doesn't matter what the key variable is, right? You can put complete rubbish in that key variable. The radios will see that these 3 values here match, and it accepts it as actually having the right encryption key. So we can sort of demonstrate the effect to the end user when this happens. Sort of sounds like that. So when the users on the network hear that, by the way, that's just a basic test. This is transmitting encrypted data, and this is receiving it on a clear transmitter with a clear receiver with no encryption key in it, so it doesn't know how to decipher it. It basically sounds like crickets in a blender. It's quite an annoying sound. It's kind of like, will it blend? So what happens then is they assume that because they're hearing these noises and it's coming from a valid radio ID, there must be wrong with everyone's encryption. So what do? They turn it off. All the users assume there's an issue, and then they turn the encryption off and go back into the clear just to ensure that someone's not trying to get a safety message through, or they just want to make sure that communications can resume fine. So this kind of leads on to the next bit, physical security in a keyloader. The keyloader is the device that actually puts the keys into the radios. I'll go over this fairly quickly because it didn't really lead anywhere. So once you've got the keyloader, you can buy them off eBay quite cheaply. You put your encryption key in it, you hook it into your radios, and then you can insert encryption keys as needed. The keys are transmitted over a wire in the clear. It just basically uses a 4000 baud serial connection, and there's no security on it. You've got the keyloader, so obviously you have physical control of the keys. So there's no other security around it really. I hooked up the output of an old keyloader that I had years ago to a DSO and looked at the handshaking. That was the initial call for the keyloader looking for a radio. So we plug a radio in and we get the call and the response. So it basically says, yep, I'm here, I'm waiting, and I'm ready to be keyloaded. That's the setup. You can see wires and all sorts of stuff hanging out. That's a really old photo, that one. That didn't really get anywhere. I didn't really learn much from that other than you could see the actual transmissions on the wire. I didn't know what they were at the time or anything like that. Then I hooked it up to a logic analyzer, and using the asynchronous serial setup, we could start to get the opcodes and start to actually determine what traffic was going across the wire. We loaded a test key, and you can see it right here in the clear, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it was kind of cute to check that out. It's not really a security flaw because once you've got the keyloader in your possession, it's game over anyway. You've got the keys in your hand, so you don't really need to worry about sucking things off the wire. So yeah, like I said, you need physical access to the device, so it's not a real attack. These devices in the real world are probably locked down in safes with people, you need to get two different people that know half the code to actually get access to it. There's no inherent security in the interface, but it doesn't matter. Authentication would be good. The newer keyloaders do actually have a key built into the keyloader and a key into the radio, so basically the transfer is encrypted, so you can't keyload radios that aren't already authorized for that particular device. And that's something that's sort of coming in now with the new tier radios released about 2 years ago. One other thing on the project, we released a paper at SecureCom 2011 in London. All of the stuff on the cryptographic research and the DOS attacks is all in that particular paper. So you can go to the NICTA website and download it. It's nicta.com.au. Search for my name or Stephen Glass or APCO P25, and that's the name of the paper. You can grab it and have a read. Now we're on to this one. Earlier on this year, we saw this appear in the Telegraph, which isn't exactly the finest in the media. It's pretty trashy paper, but high-tech hackers cracked New South Wales Police $22 million encrypted radio system. So what was this all about? Well, basically they found a bunch of tow truck drivers and bikies out there that had radios and they were listening into the encrypted police channels, this is obviously a worst-case scenario, right? This defeats the whole purpose of the system, and it's bad for everyone. Yeah, it's disappointing to see bad things happen. So I had a look into it. This particular problem predates our research. They said that a tow truck driver who had been in possession of a radio for more than 2 years said their radios have gone dead. So that's 2 years prior to when the article was being released, which means that the key had been leaked since August 2009. And for 2 years they had their key out there in the wild and no one did anything about it. Shows that they're not rolling over their keys often enough too. If you're using old encryption like DesOFB, which can be, brute forced in 2 or 3 days, as previously demonstrated, you need to roll the keys over, in less time than that. And we originally made our research publicly available 12 months ago at Ruxcon 2010, and that was the first time that we know of that anyone had broken it. Yeah, quote number 1, they said that the strategies of their key management and effectiveness are regularly reviewed. Quote 2. They've then gone on and said that it's not until they found out the bikies had it, and not just the towies, that the police acted. So on the one hand, they're saying that the strategy and effectiveness of their key management is being reviewed, but they had a leak and didn't do anything about it until they found the bikies had it. So really, if I was managing that system, or if I found my encryption keys on my web servers at work had been leaked, it'd be an immediate change, like it'd be an emergency change straight away. I wouldn't sit there and wait until the bad guys started doing bad things with it. There's another bit of technology, P25 authentication. The trunked radios, there used to be no authentication when you logged into the network, and this is something they've just introduced in New South Wales right now. So it's basically a cryptographic challenge. The radio sends a registration command. The network sends back a challenge, which is a random number encrypted with an AES 128 key. The radio has to send back a response, and then the infrastructure checks that against its own internal database and makes sure that that challenge response is valid, and then the radio can be authenticated. Do you want to do the demo? Yeah, let's do the demo. Yeah, let's do it. So we had a demo going. That's all some pretty heavy theoretical stuff that's a bit boring. What we wanted to show you was, in GNUradio, we basically implemented a full P25 receiver that can do voice. Yeah, so what we've got down here, we've basically got a Python script which runs the GNUradio program that Balance set up. The next parameter tells to tune the actual front end to 434 megahertz, which is what we're transmitting on the 70 centimeter band. And this variable here at the end is our encryption key that we're using. So this key's been loaded into this radio. It's our test key that we use just for test purposes. It's not important, it doesn't carry any real traffic other than us doing tests. And we're just going to show that we can transmit audio from P25 radio in encrypted mode. The USRP will receive it, it'll go through the GNUradio stack, it will get decoded, demodulated, decrypted, and then transmitted through the sound system, hopefully. So It's not really working too well. It's
1, 1, 2, 1, 2, audio. So you can sort of hear there's a bit of latency there. This is encrypted mode. This is what you hear on scanner. It's going through GNUradio. The traffic is coming through nice and clear. And one thing we want to demonstrate is that the silence values do come through.
When the radio was dekeyed, those last 4 values are all exactly the same after they're encrypted. So we'll also demonstrate the Wireshark plugin too. You got that open? Okay. Yeah, so you can go through and basically see the traffic. You can see each particular frame, the LDU1 and 2 frames that I talked about before, and down the bottom you've got the actual data itself. You can actually open up. You can see the network ID. You can see the raw encrypted vectors and any other information that's basically transmitted across the P25 channel. Yeah, cool. So this sort of leads us on to the very last part of the presentation, subframe jamming. This was also done by the University of Pennsylvania guys, Matt Blaze and Sandy Clark. They invented an active attack which it listens to the transmissions and then selectively decides which ones it's going to jam. So you're not just jamming an entire channel like you do with traditional RF transmitters. You can jam a particular radio, you can jam encrypted-only transmissions, you can jam only a specific user group's transmissions. It's quite smart. Basically, you've got a machine here, it just listens to the frame sync. Once it finds the frame sync, it goes down, does a whole bunch of other stuff to get synchronized. And then when it's actually synchronized with the transmission, you can then go on and transmit over the top of it if it fits your criteria. And they did it using a $30 kids toy. They got this, it's called the GirlTech IMME, the GirlTech Instant Messenger. $30 worth of toys. It's got quite a sophisticated RF chip in it, and it's actually used to send text messages between kids. If you don't want to have a mobile phone, you buy them 2 of these things. So they basically used that to implement the jamming attack. Anyway, that's it.
Anyone have questions? Questions for Matthew? Oh.
Matt, great talk. Thank you.
Thanks.
In Victoria, would the Victoria Police have data terminals in their cars? And I'm just wondering if the data, if you know, is the data related to APCO P25? Do they do data transmission as well? And is that in other states as well? And how vulnerable do you think those systems are?
In the specs, there is provision to have data over P25. It's called IVD, I think Integrated Voice and Data. Motorola in the States is sort of fairly big on it, but to be honest, I don't know what they're using down here. I know their voice traffic is AES 256 and it's fairly heavily secured and whatnot. I don't know if the data terminals are actually integrated with that. Couldn't tell you, sorry.
Hi, yeah, great talk again.
Cool.
And I asked this question last time when you were in earlier stages of research. Can this attack be implemented cheaply with amateur radio equipment and a PC? Rather than the $1,000 plus quote you gave me last year?
Absolutely. Max, the DSP engineer, he actually did just that. He got a $20 scanner. I think it was like a 1985 model analog scanner. Tapped the discriminator, fed it into the sound card, and used the sound card as the AD converter. And yeah, it was basically very cheap, and it works quite effectively for receive.
G'day. Towards the beginning, you were talking about the Motorola patent that was seemingly designed to allow you to break the encryption. There's obviously got to be a I guess, a real reason they've got that? Do you know? Can you think of any good reason for them to have that? Or
there is. Is this still doing audio?
I think it's still on.
Yeah, there it is. You can hear it. So the reason for that is they want to mute the start and the end of each transmission. If the transmitter or the receiver is slightly out of sync, you get this effect. 1, 2.
1, 2.
So at the start of each transmission, you'll get a hideous bit of noise, and you can get it at the end of the transmission too. And to the word of the patent, that's what it's protecting against, yes. So that essentially, that's what it's for.
Anyone else?
What key management practice would you recommend for law enforcement and people using these systems?
A budget note. If you've got no budget limitations, over-the-air rekeying with AES 256. And the network will automatically send new keys out to the radios on whatever basis you want. You can send them out every 24 hours. And the keys are sent over an encrypted mechanism. So no one can actually sniff those keys. The keys are sent completely secure. And if a handset gets lost, you can basically switch that handset off, stop it from getting key updates. Even if using AES 256 with over-the-air rekeying, like AES 256 can't be brute forced at this stage. So, you know, if you from a theoretical point of view, if you're swapping AES 256 keys every 24 hours, you're impervious to any attack from cryptanalysis.
So the Inhibit system, it seems on the surface a bit stupid, but I can kind of see why they did it. How would you fix that, if you could?
Authentication. The same authentication mechanism that we saw back there to prevent rogue radios from logging onto a network could also be used to do a challenge response before the Inhibit command's accepted. So you'd basically extend the protocol so that it says, hey, I'm going to inhibit you, here's a challenge response, back to the infrastructure rather than the other way. And then once that's passed, then you could inhibit the radio.
That would only fix, like a stolen radio, it wouldn't fix a malicious radio, right?
It'd fix any radio, because the authentication spec is based on having a unique encryption key for each radio, and that's got to be inserted into the radio when it's commissioned on the network in the first place. So a malicious radio, someone that's come off eBay or a second-hand one or once been purchased not through the main channels, it won't have that authentication key in it, so it won't be able to talk back to the network.
Have you had any chance of opening up the radios and seeing what physical protections are there for the keys inside? And
yeah, we have. There's a little bit. To be honest, it was a long time ago I looked at it, but each module is NIST certified. It's got to go through certain standards, like the random number generators have to be, they have to be truly random. They monitor the battery voltage, so if there's battery voltage fluctuations from a side channel attack or something like that, they dump their keys. There are protections in the radio, like to physically protect the memory that those keys are stored in. And it's stored in an encrypted database in the module itself too. So even if you pull the RAM chip off the board or something like that, it's still encrypted with a key that you don't know what it is.
Anyone else?
From memory, last year you mentioned that the Inhibit command was basically, the uninhibit command was basically just a bit flip attack. You could use the same keys for the Inhibit, reverse them, send them in and uninhibit the radio. Does that still hold true, or did I get that wrong?
You've got to be careful with the terminology. It's not a key, like there's no encryption on that command. It's basically a TSBK, a trunking signaling block, which is a command sent to the radio to do certain things, like change frequency, change channel, or inhibit or uninhibit. And I think from last year, there's only 1 bit difference between inhibit and uninhibit. So to kill a radio, you've only got to flip 1 bit to bring it back to life. Yeah.
Is that it? Cool. Ladies and gentlemen, Matthew Robert.